All right, so welcome back, and now we start to discuss like I would call basic models. And the first one is one I think you are, I'm quite certain that you're already aware of or that you already know, and it's the linear regression model. But we'll go through it, and probably we'll do it with a perspective that is a little bit different than in maybe the statistics course where you heard about the linear regression model. So, as I said, when it comes to supervised learning, we typically face either a regression task or some kind of classification task. In the regression task, usually the target variable is some arbitrary numerical variable, such as a house price or the money that we spend for rent or something like this. And the model itself is just weighted sum of feature variables. So this means here you can see the example with only one feature variable, and the impact of the feature variable for the prediction is weighted by a parameter. And also typically we have a constant in the model. This is given here by setting the first feature variable equal to 1 and using this parameter as the constant value. And in the beginning, it always makes sense to visualize this, especially as long as we are able to visualize it. So as long as we are restricted to 2 or 3 dimensions. And as you know, or as you can see, depending on this form here is an affine transformation or an affine function. And it exhibits a linear relationship. So as you can see best what's meant by this here visually. And depending on how you set the parameters, the intercept as well as the slope changes of this linear functional relationship. So if you increase the intercept, for instance, this leads to a parallel shift here. And if you increase the slope of this function, then it just increases the way how the prediction gets bigger if we move one unit to the right regarding the feature variable. All right, so and this is just to make sure that you understand what we mean by calibrating. So calibration just means depending on how we set the parameters, the functional relationships between the feature variable and our prediction changes. And of course, we want to calibrate it in a way that it matches the reality in the best way. So what we typically do is that we have, for instance, here some data. So each point here corresponds to one observation. And if we stick to our example with the ice cream scoops, then we assume that there might be some relationship between the current temperature and the number of scoops we are selling in our ice cream store. So on this day, for instance, or in this hour, which is given here, was quite hot, so almost 30 degrees, and then we sold this amount of scoops. All right, so each point here represents a single observation or a single example from our OL data sample. And what we're trying to do is, when we calibrate our linear regression model, we try to find the parameter combination regarding the intercept as well as the slope of the curve here, such that it in best way is close to all the points that we're finding here. Close to all the points means that on average our predictions are close to the actual realizations. All right, and what also is very important for you to understand is that usually we will face some randomness in the data, because there is typically, especially in the field where we are at, no such thing as 100% deterministic relationships. Like the selling of ice cream scoops, it doesn't really follow a clear law, like a natural law or something. It may be driven by the temperature, like if it's hotter, then people tend to buy more ice cream. But also, if they buy ice cream depends on many other factors, and many other factors which are, for instance, not measurable, or sometimes it really may be just the randomness which leads people to either buy or not buy a random scoop. So it's really important to be aware of this. that our real goal is not really to, make a prediction model which leads to predictions that exactly match the realizations, because we know that this is not the nature how the data is generated in reality. Our aim is to meet the trend, or the average. So here in this case, so the predictions on average should be close to the target realizations. The aim is not that each single observation is close to the actual realization. This is a really big difference and an important one. That's why I'm also highlighting this in this way, right? Okay, and if we take a look at the real regression model, like what we've seen before, this is what I would say the prediction model, but the real regression model is given here, and there is an important difference to the prediction equation, because here we have epsilon, which represents the randomness. And depending on which model we are, randomness is sometimes explicitly, sometimes implicitly given, and sometimes comes along with different assumptions. So for instance, a very strict assumption for the linear regression model could be that we assume that the randomness the shape of randomness can be represented by a normal distribution function, by a normal distribution, right? And okay, but that's important. So we always have two components, at least in our model. One is the deterministic part, which is given here, and which is our intention for modeling. So we try to model the deterministic relationship, or the fraction of deterministic relationship which may be present in the data. And the second component of the model is given in the randomness. Okay, now to make this more, we bring this into a more general framework. This is if we have more than one feature variable, which makes it then hard for us to visualize, because if the number of features exceeds 2, then we are in more than 3 dimensions, which we obviously are not able to visualize. But this is how the model looks like if we have n feature variables. And please make sure to become familiar with the vectorization of the model. So if we write it in this way, you should become familiar with what is meant by this. Okay, so the typical situation for us is we have a data sample, or many data samples, like a data set, including, 1,000, 10,000 sample realizations. And we have decided to model the relationship between the target variable and the explanatory variables with the linear regression model. So the next step is to wonder which parameters should we use. And obviously we could just use any arbitrary parameters, but usually this will not guide us to a very good model. So what we try to do is to adjust the model parameters such that they fit the data we are observing. Like that for the data, for the sample realizations that we have, we try our best and fit the parameters such that we really are able to capture the deterministic relationship in the observations that we have. And to do this, so this is the first step. It's important to say that obviously at a later stage, once we estimate our model, we want to make sure that the parameters that we estimated also work for unseen data. But in the first step, let's assume we have a certain amount of data. We try our best by adjusting the parameters in the best possible way to this data. And to do so, as I said before, we use a loss function, which is minimized by choosing the parameters. And the loss function gives us a feedback if the prediction is close to the target realization or not. And if you think about a common regression model, I think it is reasonable that we take a look at the actual realization and the difference between the actual realization and our prediction. And as we are looking for to generate a model for more than just a single realization, we would like to average the differences between realization and target variables. Averaging something always comes along with building the sum over something. But if we sum up, over positive and negative deviations between the target and the actualization, then this can lead to false implications. This can lead to, you know, like very low amount for the sum of deviations, even though we might have extremely high positive and extremely high negative deviations. So what should be done, or what needs to be done, is to at least take, for instance, the absolute values of deviations. This will be possible. What is more common, and which you already probably have seen and are aware of, is to use the squared deviations between the predictions and the actual realizations. And why use the square and not the absolute ones? The answer here lies more in mathematical attributes, because the mean squared error, or the sum of squared deviations, is a convex and differentiable function. This is not meant to tell you quite a lot at the moment, but just that you already heard about it. Using here the sum of squared deviations is rather a mathematical relic. It's also possible, of course, to use the sum of absolute deviations in order to get the feedback if we have target predictions which are close to actual realizations or not. But anyway, the higher, for a single observation, the higher this value is, the feedback is here that the more far away our prediction is from the actual realization. So this is what I mean by a loss function and what I mean with feedback, all right? And as we want to as we want to calibrate the parameters such that the model is really on average good for all the observations, we also take a look here at the average amount of deviations between predictions and actual realizations, okay? And this is like the mean squared error, and this is the appropriate loss function for a typical regression problem. There are other loss functions which can be used for this kind of problem, but I would say the mean squared error is like the most common one. Okay, so depending on which parameters we use here, the mean squared error for the whole data set is either higher or lower. And what we try to do, if we match the parameters in the best possible way to the observed data, of course, is to minimize the mean squared error with respect to the observations that we have, so the observations that are in our data set. And this can be written in this way. So the parameters, or the solution for our problem in finding the best possible parameter combination, is the argument which minimizes the mean squared error. And in case of the linear regression model, this can be solved analytically. Here is the solution in matrix notation, and you do not really need to calculate this by hand, of course. You can do this with your computer, and there are many packages which enable you to compute this and get the corresponding parameter estimates. But, so for instance here, and this works even though we have a very small data set. So here, for instance, if we have like 2 samples for the ice cream data set, here with 18 degrees of temperature and 27, and these are the target values, the corresponding, then we get here 2 parameter estimates. And for instance, if we get a third observation with a temperature of 25, or if we want to think about what we believe is the amount of scoops that we are selling, if it would have 25 degrees, then we just plug it into the prediction equation. And now with the estimated parameters, an estimation is is always indicated with the hat symbol here. So we have here the constant value. So like this would mean we would assume to sell 820 scoops, even though it has 0 degrees of Celsius out there. So it's cold and freezing, but then the hotter it gets, the higher we would expect the amount of scoops that we're selling in our ice cream store. Okay, this brings us then to the end of this video, because I would like to explain you more about the gradient descent method in the next video. But just for an outlook, even though we have for the linear regression model the possibility to calculate our parameter estimates analytically. So this means like with a real mathematical formula, and we just need to get the data and then we plug it in and we have our parameter estimates. We will more focus on numerical methods how to solve this minimization problem. And this is due to because the more complex and the more advanced our models get, the less, or even for the logistic regression model, there is no analytical solution available. So this means there is no equation like this. And so finding the best parameters is always related to some sort of numerical optimization. And even though this may sound complex or intruding to you, then we will take a look at this in the next step. And there are different methods for finding numerical solutions for this problem here, but we will focus on one which is based on the gradient of the model, or on the gradients of the loss function, because this is a very, I think, intuitive and common method for numerically finding the parameter estimates. And this is what we're going to do in the next video. And yeah, just like one more thing I would say is what I would like to point out. Always remember, regression is estimating the conditional expected value, right? Because using the mean squared error, or because like in an unconditional way, like you already learned this, I'm quite sure, in your statistics course, for like a consistent estimator for an unconditional expected value is like the average value of observations, right? I think you already heard this. And what we do when we want to derive this consistent estimator is to minimize also the mean squared error, but without, like a functional relationship between feature variables and a target variable. We only do this for the observations that we have. And this brings us to the consistent estimator, the unconditional estimator for the expected value. And here we also minimize the mean squared error, only now in a conditional perspective. So this is the reason why the solution to the mean squared error in this way that we just defined it here is simply estimating a conditional expected value. And conditional just means here, if you go back, that it really matters if we have 20 or 30 degrees out there, because this really shifts our expectation, which is the value here, on the amount of scoops that we expect that are sold within this hour, right? So this is why we say conditional expected value. An unconditional expected value here would be probably something around here. So this means on average, no matter how much the temperature, we would assume that probably, I don't know, something here like a little bit more than 2,000 scoops are going to be sold, because this is like over all conditions, including all temperatures that we observed, like the average that we observed for all these values and for all these data points. But once we differentiate here, and once we include the dimension of temperature, then we have to think in conditional expectations. So given temperature is, 30 degrees, we expect to sell what we have, approximately 2,500 scoops. Given the temperature outside is 20 degrees, we only expect 2,000 scoops to be sold, right? So this is the only difference here. Otherwise, the linear regression model and all models which aim to minimize the mean squared error are all models which aim to model the conditional expectation for a target variable. Okay, but that's it for this video, and we're going to more into the technical details of calibration for calibrating the parameters in the next video. So take care and see you in the next video. Bye bye.